There you go.
Yeah, my computer's slow.
You get a new one.
I'll probably get a new one next year.
Mm.
Just get the most out of this while I have it. All right, let me get rid of Chrome.
Um,
Okay.
oh, here you go. See it now.
All right, awesome. So I got everything done. Am I cutting out or am I good?
Oh, wait a minute. Yeah, the screen is still like jumping around. Okay, here you go.
Is my audio good? I could turn
Yeah,
off my screen. I probably should turn off my screen anyways. It's so
yeah,
slow anyways.
that's fine.
Um,
Okay, here you go.
wait, what was going on?
Okay.
Okay, yeah. Like I was saying, okay, so I got my code finished. I just need to find a good data set to train it on. Um, so all right, let me just explain what I did. So do you see this?
Yeah, the import, right? The import.
Yeah, so these are just all the
Okay.
functions that I have to call. Pretty much like when we did when we first started doing when I first started the lab when we were just testing that paper, the code from the paper.
Mm-hmm.
Just told you with the variational autoencoder. So I looked at a lot of the functions that he used, and then I just kind of imported when I needed them. It was pretty straightforward.
Yeah.
And then I went about designing an autoencoder. Gosh, this thing won't even scroll down. But your screen's off, right?
Yeah, my screen is off too. Wonder how you do all of this.
Yeah, my mouse won't even move now.
Yeah. Oh, yeah, it's because you're sharing the screen in Zoom, right? That's what's lagging. But yeah. Mhm.
I was trying to get off something. Okay. Okay, so amazing. Okay, so yeah, so I'm just designing my autoencoder. So it's a Wasserstein autoencoder. It's not a variational autoencoder. It's quite similar. So I'm just defining the autoencoder in that it's a neural network. And then I'm starting with the first parameter is the input dimensions that describes how many nodes it has in the beginning. So
Mm.
the most autoencoders are designed to compress information. Mine is different. What I'm doing instead is I'm trying to model the compositional space. And the compositional space is pretty low information as it is. It's not like an image that has thousands of pixels. It's just a vector or a series of vectors that have basically like 10 dimensions, 20 at most, maybe.
Mm.
So, and because the compositional space is going to be one dimension smaller than the number of metals that compose an entropy alloy, my to I don't even lose any information by compressing the hidden layers by one dimension. So that's what I do here. I'm basically explaining what I just said before. Um, it's designed to model the latent space, not exactly to compress it necessarily. So I'm just describing all the layers. I use pretty much the hidden layers, all the same dimensions. And I have the option, I just go to right here, of making the latent space one dimension smaller than the hidden layers.
Okay.
But I'm not using it. I'm just having the latent space just be one dimension smaller than the input compositions.
Okay.
Um, so yeah, so then I'm defining my non-linear function, and then I'm defining my normalization that I'm going to use. And
So
so
wait, so
here,
for the structure, so what's the dimension for the input?
um, I don't define it. It's the thing I
Oh,
input to the network. I'll explain
oh,
later. I
okay.
actually create a function
Okay.
later on that reads data and then tells the network what dimensions the data is.
I see. Okay. And
I'll get
then
to the at the end.
for the, okay, so input and output again. Then for the hidden layer is one dimension lower than the input.
Yeah, and it's
And
just
then,
I'm not necessarily trying to compress any data as much as I'm just because like when you have three compositions, how it's like a triangle, how it's two dimensions when there's three different components,
mhm.
how it's one dimension smaller than the number of materials that you're mixing. So
Okay.
no information is lost by doing that. So and I don't want to overfit it, so that's why I do that. And
Okay,
then,
I
so this is
see.
the base. Yeah, so this is the basic skeleton of the neural network, and then I'm defining my nonlinear function, and I'm defining my normalization.
Okay,
And then I'm
I
defining the
see.
autoencoder. So I am doing the activation function after normalization, and then this is the layer. And so each layer is a function of the previous layer, and then I create the this
Okay.
is z of x, that's the latent space,
Mhm.
and the decoder takes z of x and then takes x of z, which is supposed to be my reconstructed input.
Okay.
And then
And
so this is my
for the
yeah,
latent
go ahead.
space, how many dimension is the latent space?
One dimension smaller than the input. It's the same dimensions as the hidden layers.
Oh, okay,
I
okay,
have
okay,
the
okay.
option of making it smaller. If ever I need to, I could always define it smaller than the hidden layers. But right
Mhm.
now I'm not doing that,
Okay, I see.
just in case. But I'm not doing it. And then so I tested it first with random numbers. So I create X. What I did was I had supposed to be 10 elements, and there's varying compositions. And forget how I did this. I think I didn't even make sure they all added up to one. That's a problem. I just had them random variables between 0 and 1. But in real life, they'd all have to add up to 1. I just noticed that just now.
Mm.
I'm gonna have to change that later. But anyways, I just had compositions ranging from 0 to 1, and I had a vector of 10, and I have 100 of them. So it's pretty much like I'm running on 100 samples of compositions. And then L, that's supposed to be the number of samples I have, and then input dimensions, that's just how many dimensions my compositional space is.
Mhm.
And then so X is the compositions, and then T, that's supposed to be the property that that composition has, and that could be with anything.
Okay.
Um, like the paper we're looking at, that was TEC, but it could be any way I define it. Does it make
Mhm.
sense so far?
Yeah, makes sense so far, yeah.
Yeah, and then this right here, this clone detached cross grad, it's just a way of formatting the tensor so that it can be read by the loss function.
Okay.
And then here I'm just making sure that T is a vertical vector.
Makes sense. Okay.
Okay, and then I'm defining, because I'm using the Wasserstein distance, I'll explain later how I cluster stuff in the latent space. So that's the strength that I use. And then mu. Okay, so what I'm pretty much doing is in the latent space, it's not that I'm trying to just have the latent space be any combination of the inputs. I'm trying to make sure that I'm mapping everything onto a sphere, and the sphere or a hypersphere. So it's a hypersphere in 9 dimensions, in this case.
Well,
And what I do is that I make sure that stuff with better, more desirable properties will be mapped to a smaller sphere, and stuff with undesirable properties is mapped to a larger sphere. And so the goal is to make the latent space learn how to, and I want it to be able to interpolate to extrapolate or interpolate possible compositions that will have good properties, and those should be in the middle. So then the goal is after training the function, I'll then just sample from the center of the hypersphere and generate a bunch of candidate compositions that could be tested in the lab. That would be a better guess than just guessing at random. Does that make sense so far?
wait, hold on. Sorry, I maybe forgot some concept that. So, how do you know the position? Because it's a sphere, right? And you wanna the
Hypersphere could be any
yeah.
dimensions, but yeah,
So the composition that have the property we want will be more in the center of the sphere, right?
correct, yeah.
But how do you
Because
define the coordination of that composition?
what I do is so the Wasserstein distance would map something to a distribution. And so I'd be mapping the compositions to a shell, a spherical shell.
Okay.
And the better the properties they are, the smaller the shell that they're going to be mapped to is. And so the
Okay.
point would be that it would create this hypersphere where the good stuff's in the core and the stuff I don't want's out in the periphery. And I'm just going to sample from the core when I generate stuff. or generate compositions.
Okay.
Does that make sense?
So you have two set of data then, right? One is for the composition and the other one is for the shell.
Well, X is the composition, and the T, that's just the input of the properties, material properties, and then I'll explain later tau is the target, and the goal is to get stuff with T values that are close to tau. Is stuff that's going to be tried to be put in the middle of in the middle of the sphere.
Oh, okay. Yeah, then let's move on then. Maybe I'm gonna
Yeah,
understand it later. Okay.
yeah. So mu, that's just the radius of the sphere. If I'm just ignoring the properties or the material properties, and then tau, that's the target value, and then T, this is a bit complicated. I'm essentially creating a function of how different the properties are from their target, and then I'm going to multiply this by X, so that I don't know. I'm going to multiply that by the latent space values, so that the Wasserstein's distance thinks they're further away from thinks that the good compositions are further away from the sphere than they actually are, and so that it would inadvertently map them to the center because it's trying to map them to a shell, but it thinks they're further away than they actually are, and so it inadvertently puts them near the core. Does that make sense? It'd probably be better if I had visuals. I will when we have
Yeah.
the meeting on Monday.
Yeah. That's why I think that's one of the reasons PyCharm is not very well used in the lab, like among other graduate students. Yeah.
Why? Because it's hard to visualize?
Yeah, because like because I work in the lab, the max area with other graduate students recently, and most of them use Microsoft Visual Studio. So it's like Jupyter Notebook, basically, a Google Colab. It's very easy to like explain to other people.
Yeah. On Monday, I'm gonna make visuals on a slide, and then after I explain my just conceptually what I'm doing, and then I'm gonna go into and show the code what I've done so far.
Yeah.
And so people will track better because they know what I'm talking about. But I haven't made the
Mhm.
slides yet.
Yeah.
Okay. Yeah, so pretty much just overall, this is loading data that I have. This is defining the distribution in latent space. And then this right here is defining the parameters of how the thing learns.
Okay.
And so this is very simple. I probably can make this more complicated later on, but I'm pretty much just doing very simple batch normalization or batch, what is it called when you do gradient descent, like batch gradient descent? I think that's what it's called. Yeah.
Back propagation. Yeah.
Well, there's three varieties. There's stochastic, and then there's mini batch, and then there's batch. And mini batch tends to be the best balance between the two. Batch takes the longest, but since my data is so low information as it is, I don't think it's a problem to use uh, batch learning because the load times aren't really a problem.
It all depends on batch size though, depending on the size you set it. So it doesn't matter.
Yeah, because I'm training it on a batch size of only 100 because that's how much data points I made. But in theory, I'm probably going to be training this on a batch size of thousands or more.
Let's see. But the
Um,
bigger the batch
so
size, the less accurate it is though. So
I'm gonna have to probably learn how to
yeah,
add more functions. But this is just a very simple, just so I know what I'm doing,
yeah.
just so I have something ready.
It's a hyperparameter. You just have to play with it to get the batch
Yeah,
result. Yeah.
yeah. So my learning rate is this. It's very small. I train it routinely on 10,000. It doesn't take that long. I'm probably just gonna make it 1,000 just for a demonstration
Well, that's
because
a
you know
lot
I have
though.
all the time in the world.
Yeah, 1,000 is a lot. Yeah.
Yeah, I learned slow though, and then so yeah, this is just setting out the loss function. Um,
Mhm. What's your last
so
function?
yeah, I'm using BCE loss, which can work for compositions because they're just between 0 and 1, so it doesn't really even though it's often used for probabilities, you can use it for that. I probably would use MSE. I think either one would be fine.
Mhm. Okay.
And okay, this is just okay. This is probably going to be harder to follow along with. I'm pretty much now these are Z values. This is for latent space, where I'm tricking the thing into thinking that the desirable compositions are further away from the center than they actually are. I'm tricking the Wasserstein distance. Okay, so this is a bit complicated. So you know how Wasserstein distance is very complicated mathematically,
Yeah.
especially if I'm working with like a 9-dimensional sphere. And I have to
That's
define the surface of the sphere.
okay.
Instead, what I just did is I converted all the 9 dimensions into a one-dimensional vector for the absolute values, where 0 is the center of the sphere, and then further out is just the distance away.
Oh, okay. So
I'm
it's just the absolute distance now instead of the
Yeah, so it's
coordinate.
just
Okay.
I'm only doing Wasserstein distance in one dimension.
Okay.
Another way to simplify it too is that the target distribution is not a distribution. It's actually a shell that is it has no depth. And so I'm essentially mapping a kind of a messy distribution onto a point distribution in one-dimensional space that represents a shell of a nine-dimensional sphere, a nine-dimensional hypersphere. So I don't even need to calculate the transport plan. All I need to calculate is the absolute distance. And so it's actually extremely simple, and it works no matter what dimensions I have.
Mm-hmm.
And so I just calculate the Wasserstein distance. This is pretty much just the absolute distance between the hypothetical sphere I'm creating and the data points that are corrected. And then so I do backpropagation. I have the loss function, and then I have the Wasserstein distance, and
Mm-hmm.
then after that I print everything. So I'm gonna
Okay.
run it right now.
How long does it take?
Shouldn't take too long. Hold on.
Too much. The return.
Okay, it should be running now. Yeah, it runs through really quick actually.
Oh,
It should
yeah.
only take probably like 2 minutes.
Oh, wait, that's a lot. Okay.
Oh,
Oh, here you
so yeah, this part right here, this is yeah, this is the loss distance, the loss function, the first value, and the second one is the ratio of the loss function over the Wasserstein distance.
go. Okay. We're going to try to move in line. The loss function. Okay.
Okay, so what this graph shows is that this is the absolute distance, and this is the properties I have, and my target is 0. So the goal is to get 0 to the center of the sphere. The random values, it's hard for it to model the random values, so it doesn't do a very good job.
Mm-hmm. Yeah.
The goal would be for this to be a perfect line. So I might have to make some changes or fix some stuff. But there is a little bit of a correlation you can probably see. Um, if I made the lambda value higher, I probably would get a stronger one. I've got some pretty close values before. But yeah, that's pretty much just the concept. So I have a lot to go from there.
Yeah.
Let me just try it with a stronger value of lambda really quick. I'll speed up the learning rate too.
Mhm. 0001 is a popular learning rate though. I see it everywhere.
Hold on, that's just because I restarted it.
Did you read the email Cal sent us?
The one we're meeting on Monday?
No, the one that with the national lab on the research
No, I haven't. I
opportunity.
haven't seen that.
Okay, you should look at it. Yeah,
Okay.
interesting. Yeah.
Yeah, this is loading a lot faster now.
Mm-hmm. Wonder how accurate it is though.
Well, this is just a proof of concept. I'm modeling pretty much a random vector. It's there's literally no pattern in the space it's trying to model.
Uh,
Yeah, this isn't very good. But yeah, maybe when I test it on a real data set, I'll get better values. But this is pretty much just what I have so far. So I'll stop sharing. Wait, do you see my graph actually?
Graph?
Wait, can you see my screen?
Yeah, I did see the screen of the pie chart, but I didn't see the graph.
Oh, you didn't see the graph afterwards? Oh, darn it. I'm sorry.
Okay, yeah. It's pretty hard to tell.
Yeah, I'm sorry about that. Okay, do you see this?
Okay, here you go. I see it now. Yeah. Oh, you
Okay,
were
so
talking about
this,
this. Okay.
yeah,
Okay.
yeah. So you can see there's a slight correlation. Ideally, it would be a line. That would be the ideal, would be a line right here between
Mm-hmm.
absolute values and properties, but I don't have that because
Oh,
essentially it's trying to model completely random values. But if there were a pattern in the data, like if I trained it on a real data set, I might get some results, but we'll see.
okay. So,
So yeah, that's what I have so far.
okay, I see. So the probability, no, not the probability, the property that you want is gonna be have a less radius. So it's gonna be more on the left side, right? In the graph.
Yeah, I
I
had it
see.
set at 0, so 0 should be in the middle. So there would be a completely linear distribution. But if I had maybe
Oh,
it set at 6, maybe ideally it would be shaped like a V.
okay. Okay.
But yeah,
Interesting. Yeah. But that's very different with um the TensorFlow and Keras, but yeah. Anyway, and
yeah, I'm
then
working with PyTorch.
oh yeah, Pytorch, yeah. I'm gonna ask Cal this question on Monday too, because I finished with Keras, but I'm not sure because Keras go with TensorFlow, but should I choose like either TensorFlow or Pytorch? And I'm still wondering on that. If I
Yeah.
can ask him on Monday, yeah. Yeah. And then
All
yeah,
right, who would
Phuong,
like to go next?
Phuong, you're gonna go next.
Alright, can you let me share the screen?
Oh yeah, the privilege.
Oh, sure. Oh, that's right, because of the security thing. Okay, you should do it now. Oh, by the way, I saw your presentation from last week, just so you know.
Oh, right. So I will present about autoencoders.
Oh yeah,
Uh,
sorry, just for the context. So Phuong just representing the model that we already learned, just for her to learn the new models and stuff like that.
Oh yeah,
Because
yeah, I did that.
yeah, I've really just give them like a month to catch up with us. And so you're gonna just see her repeating. You already know, but just
Yeah, yeah.
just
All
for
right,
the
sounds good.
purpose. Yeah, yeah.
so I will go to the definition. Unsupervised deep learning algorithms for reconstructing the high-dimensional input data, and the main goal is to approximate the distribution of the input value as accurate as possible. So basically, this is the diagram of the autoencoders. So we have the input and the output, and this one is encoder network will compresses our input into a lower dimensional representation and store in the bottleneck layer. And then it will the decoder network will take the data that we store in the bottleneck layer to reconstruct it as an output. And most of the time, the output would be like similar to the input, but not exactly the same. Due to there will be some reconstruction error, so the output cannot be exactly the same as the input. So the data should have dependencies across dimensions so that we can use it to for the encoding and decoding. If not, we can it is impossible for us to do that. And this is an example that I find about how the autoencoders work. So this is an image that we put in as input, and then the encoder network will compress it into the lower dimension and store it in the bottleneck layers, and then the decoder network will take it and reconstruct it as the image. As this is example of the output. So as can be seen, like it's not the light is darker, so it is not exactly the same. And this is how the autoencoder works. Like it's not really the input, but it's somehow like similar to it. And the reason for that is because during the process there will be the reconstruction error. So the reconstruction errors will measuring the difference between the input and the output. There's two diagrams that illustrate the idea of when the reconstruction error is low and when it is high. So when it's low, it can show that the input and output have the same path as each other. However, when the error is high, so it means the output cannot it's really different from the input. Like you can see in the diagram, it's really different at every like part is different. It's not like the reconstruction error. So the next is another example of how different when the reconstruction error is low and high. So if we have a small error, the output is still somehow like represent the input. So when it go through the encoder and decoder, it still generate the same input. However, when the reconstruction error is like too high, so the output is not, it cannot like, the output is just doesn't like the same as the input. And that is how different. And in order to make sure that the reconstruction errors is low, we have to train the autoencoders using the back propagation to minimize reconstruction errors. And we also need to exclude the less useful feature and transform the data, like the most important data, to store in the bottleneck layers as a lower dimensional representation. Because when we do the exclude the less useful data and transform them, the main information, we will prevent the overfitting. So overfitting means like it take all of the data, but not eliminate the least useful one. So here is the example of the denoising sound. And we have the original sound, and we add the noise in there, and we put it in input. Then it will compress the sound into the lower dimensional data, and then it will decode it into the output by like cancel out the noise that we already add as the input. So the reconstruct output will somehow like similar to this original one. So it will not have the noise that we add at the beginning. And another application is image denoising. So it works just like how we denoise the sound, but with the image. For example, here we have the image with some like noisy spot in the image. We cannot like see the image clear, so we will use the autoencoder to encode it and then decode it and reconstruct it at the input. So we have the clear image. It's somehow will not like if we compare to the reference image, it's not the same, but we can see it's clear and it will not have some like noisy dot like here. And the next application is anomaly detection. So we can detect when the machine has problems, so we can fix it, and we can compare the output to the input to see where is the machine have the error or the wrong part in the machine, so we can find it and fix it. So yeah, and there are many other applications, but these three is the most like people we use the autoencoder to like denoise the image sound and detect the anomaly. And yeah, that's pretty much my presentation. And this is my source. And yeah.
Yeah, nice. You have any question, Ethan?
That was pretty good. It kind of reminds me when I first started. Like, there's a lot to variational autoencoders that is very confusing, and also like there's many different kinds. Like
Mhm.
there's like you might have run into these on your way about learning about them. They're called variational autoencoders. It's kind of the variant that I'm using. Those are used mostly for denoising because they have a very smooth bottleneck space. They're just called light in space. So yeah, but yeah, seems like you're on the right track.
Yeah, makes it weird. And then I remember after this, we read the paper. I can show you the paper. Paper is actually in the Schoettler drive, and you can go to documentation. I don't know, documentation. Read the paper, and that is this one right here. And this was the paper you read. Could be the link for you too. Drive. Share. Here's the link. Oh, yeah, yeah. Just read over the paper, and I don't know. Doesn't matter if you understand it or not. We will over it next time anyway. Copy link. Paste it here. But yeah, basically, in most cases, just focus on the abstract, and then just read the introduction. But we're gonna be focused on from this stage to this stage right here, the latent space sampling. And only the first two stage, and we don't really care about the rest. Just focus on this. And then also focus on this figure right here. This is the latent space in Autoencoder. And that's it. The rest doesn't really matter. Yeah. Just read over it. Yeah. Then we can go over it next time in the next weekly meeting. Do you want to meet next week, by the way? We have a meeting next week, yeah.
I could set up a meeting for next week.
Okay, yeah. And then it's my turn to present. Where am I? So for the last time, let me get the code first. That is alpha. Here you go. So the last time I'm presenting this. This is the so I did on the neural networks, and I did a dive deeper into it. And I have a big picture, a pretty good big picture already from Max with Illumini. And so from that, I want to go deeper. And the next thing I learned is the underlying mathematics or motivation in the neural networks. And for that, I did the neural networks from scratch. And it was very helpful. I finished that. It's only a few hours, 3 hours. And then when I finish that, I want to continue with that neural network just to go deeper. And I also want to do the coding and the actual code for the neural networks. And so I learned Keras. It was recommended from Cal. And this is the actual code. I probably explained some of them in the last video already. I'm going to go over them again. So in this code, I actually hard code the model myself. So just like you've got to specify very specifically, you specify the layer, how many neurons in the layer, what activation you use, what's the loss function, and things like that. So I actually hard code the model myself. And this is just a bunch of import. It's the same as you, doesn't really matter. And then this is GPU to train the data. So I use my computer. So if you did it on Google Colab, it doesn't really matter because you can use their GPU. reviewing on your computer, and I'm using on my computer. I'm using GPU on my computer to accelerate the process, which is not very necessary, but in the future it will be necessary. And this one is look at simple code, but it's not that simple because this code doesn't really matter. You have to do a bunch of other stuff to get the GPU to be compatible with TensorFlow, and you have to download the specific version of TensorFlow, specific version of CUDA, CUDA CNN, and other stuff. Has to be the correct version. It's older version, and then you can do other stuff and then make it into the key directory and stuff. And eventually you have to restart the whole computer to get the GPU to work with the code. It was pretty complicated. But I got the video in the Discord channel. I'm gonna check that out. But it's not very important, by the way, for now. It's not that important. And then next what I do is organize the data. So it's just you have the folder, and inside the folder there's image. And instead of make it kind of random, I make them organized in a specific way. And also the name of the folder is also become the label for that data. So it's just more convenient, specifically for image processing. And this one is pre-process the image. So I specify the path for the train set, the path for the validation set, and the path for the test. And the difference between them is that the train one is the one that you actually use to train the model. The validation one is just a few extra one you use to test the overfitting problem. And if you see, for example, if it learned the train path very well, but doesn't learn the validation path not very well, then you have an overfitting problem. And you also have the test path, which is in the end, very end, you have a thing called confusion matrix. And this you're gonna see, this gonna test to see how well is your model. And so I create the batches. This one I specify the model I'm using and the directory. Also this is the dimension of the image. So how many pixels is it? And what's the label for it? And then also specify the batch size. So this one is depend on if you do it too high, that it's processed really quick, but it's not very accurate. If you make it too low, then it's really slow to process all the data. And then this one is to visualize the data. It's not very necessary. I just call it out to like just to look nice and see how computer view it. So I just put it out. It doesn't really matter. And then this one is where I actually build the architecture of the neural network. So the models is sequential, so it's paths forward. It's not recurrent neural network. It's not going back. It's just from left to right. And then this is the first hidden layer. You only specify the input shape. Yes. Well, any question? Okay. So
Oh, wait.
yeah.
Oh, all right. So I'm trying to understand what's going on. So this uses it's formatted a bit differently than how I'm used to because I was using Pytorch.
Mhm.
So early on when you were talking about like using the GPU, like I'm a
GPU.
bit confused how that works because when
Yeah.
I was looking at my model, there were like ways of like when you're downloading data sets of like using GPUs instead of CPUs, but I never understood why that's important.
Oh, because
It,
if you ever train a big model and you use CPU, it's gonna take you like 12 hours. And if this is the same model, you use the same data set, and use GPU, it only take you 2 hours.
okay, so it's like a more okay because okay, so CPU uses scalars, right?
Yes,
And then
CPU is
TPU
yeah, vector. Yeah.
GPU is vector, and then TPU is tensor, right?
CPU is matrix multiplication or tensor, the same thing. Yeah.
Okay, why aren't TPUs used though? Wouldn't those be the best?
It is the best, but it's also not very popular. And also is pretty expensive.
Oh, okay. Okay, so GPUs are just kind of the best compromise.
Yeah, for us right now, yeah. Unless you
Are
work
those
for like
things,
Google or something, you use TPU.
do you like add GPUs onto a computer? Are they like extensions or do they come with them usually?
You can add it onto your computer as a physical TPU, a small physical TPU.
Okay.
Yeah. But yeah, it's not, I don't know, it's not very, like, unless you do a really big scale model, like ChatGPT, then TPU is good. But yeah, for us, it's GPU.
Okay, so what you're doing there is just making sure that your model uses the GPU.
Yeah, and it's going to be
Okay.
helpful in the future. Yeah.
Okay, cool.
Thanks. Yeah, here's the architecture. So you specify the input shape, then you build the first hidden layer, then the second hidden layer, and the third hidden layer. So I actually hard code every layer in here. And then I go this model summary just to give an overview of all the layers. My first layer, the first input layer doesn't specify here, but you have the second layer, third layer, and so on and so forth until the very end. So this model is used to identify whether the image that you input in is a cat or a dog. And that's why the output shape is only two, so it's only either cat or dog. And then you compile the model, specify the optimizer, in this case Adam. And it's also a very popular optimizer. It's just the very basic stochastic gradient descent. And then the learning rate is 0.0001. Again, it's a very popular learning rate. The last function is categorical cross entropy because that's the best one for, binary, choosing one or two for probability. Metrics is accuracy, just measure how accurate the model is working. So this is the fit function. And you simply start training with the fit function. You have the train patch, you use the train data. This is validation, just to make sure of the overfitting problem. The number of epochs is 10, and verbose is just how how many data do you want to show in down here? So if you put verbose equals 0, then it's not going to show anything. And verbose equals 2 is going to show you everything, all every single data. In this case, you can see this is the first epoch, this is the last epoch, and the epoch is this is the size of the data, the batch size. 6 is the amount of second. This is the loss, this is the accuracy. This is one's for the validation data, this is for the overfitting problem. And then you can see the loss decrease a lot, and the accuracy go up until almost 100%. But at the same time, the validation accuracy is not so high, and so that's where it has an overfitting problem. But I'm not so concerned with it right now because
Wait,
yeah.
okay, before you move on, I want to make sure, go up a little bit.
Yeah.
Wait, so this table, wait, hold on, the image, right below image PNG. What is this table exactly? Is this different types of data?
This one
Yes.
is a summary of the model I'm building. So it just specify what layer I having, what's the dimension of that layer, and how many parameters in that layer.
Oh, okay. Okay, so your model's way complicated. So it has a convolutional layer first.
And then the next pooling is not very complicated for a CNN, but yeah. It's kind of
Okay.
specifically for CNN, yeah. It's for image processing, but like it's not.
Okay, that makes sense. Thank you.
Yeah. Yeah.
Yeah, another thing too, I recognize the optimizer atom.
Oh yeah, yeah.
Or that when I was looking at like how to create my function, I saw a lot of that.
Yeah. And then that's okay. And then this is the overfitting problem. And I don't think I'm on the level that can fix the overfitting problem yet, so I can leave as that.
That
And
means
then
it can't predict. Is that when it can't predict new
yeah, it's not very good with new data. Yeah.
there's gotta
But
be a way of adding that to your loss function.
Yeah, I think so. Yeah, that's some ways to go around with this. Yeah, and one of the ways they generate the image, so they generate more data. So they kind of shift the data to the left, shift the image to the right, and like rotate it 2 or 3 degrees and stuff like that. And
I see. Okay.
yeah, that's how they solve it. Yeah. That's with the image. I can't know about other stuff. And then this one is test. So you want to show how good your model is. And from this little there is this very interesting thing called the confusion matrix. And this is probably one of the most valuable thing I learned from this model, which is because I saw this a lot in the graduate student presentation, but I never really understand it until now. And then there's a bunch of stuff, but it's simply just plotting this is the most important thing, is that you have on the x-axis is the predicted labels, is the result from the neural network. You have a cat option and a dog option. On the y-axis, you have is the true label, the actual label of the actual data. And then you have two labels, cat and dog. And if the predicted cat is aligned with the actual cat, this is more colorful, the color is more deep. And then this is dog, the predicted dog is correct with the true dog. Then this color is higher, and you have this diagonalized line. This is only 4 box, but like in bigger one, you're gonna see this line. And then the higher the number in this line, the better the model is. So in this case, is the number in this line is higher than this 16 and 15, so it's pretty good. But if you compare with other models, which I will show in a minute. So this is VGG16 model. And in this last model, I actually hard code the model. So I specify all the layer, all the hidden layer, how many neuron, what's the activation function, everything. But that's turned out to be not so efficient. And what's more efficient is that you go ahead and you download a famous model. So this is a very famous model for image characterizing, and it's won the competition in 2000 something already. It's really well known already. So you just go ahead and download it, and then this is get very complicated, but we don't really care. And then at the end, you just modified it into the one that you're interested in. This is the model. I copy from it, and then I just copy everything except the last layer. And for the last layer, I add my own output. And this output only has 2 neurons because it's only either cat or dog. So only 2 neurons for that. And this one, I freeze the trainables, freeze it because I want to keep all the weight and biases from their model. So I don't have to train them again. And this is the summary of the model again. It's very long and complicated, but this one is the one that I care, is that the very output is have only 2 neurons. And this is the trainable parameters. So this is the parameters we're going to train. Instead of train all of these parameters, we're going to train the parameters we're interested in. And then I train the model and everything, compile it, kind of the same process. But here you can see the accuracy started at 82%. So that's really high for the accuracy. You compare with my model. The accuracy is only 56% in the beginning, but here's already 82%. And that's the advantage of using a good model. It's modified. And also the validation accuracy is very high too, compared with the accuracy. So we can, the overfitting problem is not happening here. That's a good sign. And for confusion matrix, you can see it's a lot better than the model that I hard coded. Like you can tell, very obvious. You would have 0, 3, you have 16 and 15. This value is a lot higher too. This is a lot better. And then I did another one just for fun. is sign language. This is mobile net model. So it's the same concept. You don't hard code the model yourself. You just find a good model, and then you go ahead and download the model. It's organized. It doesn't matter. And then oops, it doesn't matter either. There you go. You modify the model. I just download it, and then I modified it just to fit to my interest. And then this one's different, but and the M in the confusion matrix is a different problem, by the way, but it performed really well just by downloading the model and modify it instead of actually hard code everything yourself. And I think this one is the future too. Like in the future, if we're gonna do like solve our problem, we are engineers, so unlike physics and computer science, if we're engineer, like we don't really care that much about the architecture inside the neural networks. Like the model side, we don't really come up with the model ourselves. Like we're not gonna come up with transformer. We're more like we know the correct model that solves our problems, and we just go ahead and download them and modify them just to fit with our problem. Well, I think how it works, but we'll see. Yeah, and that's it. That's all I have. Any question?
Wait, so how many different models have you made?
Like a lot of models. I don't know.
Okay.
Given
Are these
available.
these are technically because what you're doing is essentially it's discriminating and telling you which type of data you're feeding it, right?
What type of data? What do you mean?
Well, you're feeding it cat and dog images and it assigns labels to them. Is that correct?
Oh, that's so this one and this one is only cat and dog, and this one is different one. This one is um hand digit style language, digit number. This one a different one.
Okay, but they're pretty much what they're doing is they're taking images and sorting them into like category, right?
Yes. Mhm.
Okay, so what type of neural network is this? This wouldn't be a variational autoencoder, would it?
This is not a variation encoder. This is
What type of neural network would it be classified as?
um this one is I think it's called function model. It's kind of random, but yeah. But like I know this one
So
is sequential, which is 16 is sequential. So it's just the basic one.
okay, so they're not necessarily any category. These are just things that you made sort of independently, right?
Yeah.
Okay, interesting.
Yeah, pretty interesting. Yeah. And this is not advanced neural networks, by the way. It's just regular neural networks.
It's much more complicated than mine.
Yeah, it does. It does. Yeah, because they're a very well-known model already, and they don't just do like cat or dog. They do like 1,000 of different things. So if you input, let me have it in here. If you just have an image, like randomly image, and then you put it in, like this is a random image from Google, and I put it in and I run it, it actually gives you a probability of what the hell it is in the image. Big one is 98% of a green lizard, and it is correct. Yeah.
Wait, that's not your model though. That's something else, right?
It's not my, it's a mobile net model. Yeah, it's not my model.
Okay, because that was extremely close. It was like 98%.
Yeah, that's very crazy. Because it's already a well-established model out there, and I'm just downloading it, and then I modify it a little bit here and there, just to fit to my problem.
I see. Okay.
Yeah. So
With
this was,
mine,
yeah.
oh, go ahead.
Yeah, so for this hand problem, like the data set, this one is not in this model, in the mobile net model, but even when I solve a problem that is not in their model, they still perform very well. So that's why it's helpful. Yeah.
So you're repurposing that for sign language.
Yeah.
Okay,
Although sign language is not in the model. Yeah.
I see. I don't know if I have anything else to ask.
It's a pretty solid one though. I'm kind of curious if PyTorch have something like this because pretty nice.
I'm not sure. I went with Pytorch because it just seemed like most people are using that for autoencoders. I mean, it works pretty well. It seems to have everything I need. My model's kind of a Frankenstein's monster. It's different stuff I've seen on the internet, so it wasn't entirely on me either.
Yeah. Okay. Yeah. There you go. Right. Yeah. It's almost an hour already.
Yeah.
Yeah. If we don't have anything, then we can end the meeting here.
All right, cool. See you Monday.
All right. See you Monday.